Okay, so now um, the reason why we are studying kinetic theory of matter is because of our interest in what matter actually is. Chemistry is the study of matter, okay, and we're interested in what matter is, okay, how matter interacts, why matter behaves the way it does, okay, whether in solid state, liquid state, or gaseous state. So, and that is why we are studying this because this affects so many other things going forward. Okay, how they interact, how they react, and all of that. So now let's look at the real world relevance of KMT, that's kinetic molecular theory. Now, why does a balloon inflate when you blow into it? Why does a bottle of water eventually disappear? Why does the metal spoon feel colder than a wooden spoon at room temperature? So to answer these questions, we must look beyond the visible, okay? And we must look into the world of atoms and molecules. So the kinetic theory of matter provides the crucial link between the microscopic motion of particles and the macroscopic properties we observe every day. So that's KMT. So KMT gives us the foundation, okay, for understanding how things work around us. Now, let's look at the theoretical foundation of KMT. I can ask you to state the core postulates of KMT, and there are 5 of them. 1. Matter is composed of particles, okay, that are in constant random motion. Note that are in constant random motion. 2. These particles are separated by empty space, and the volumes of the particles themselves is negligible compared to the total volume of the substance. 3. Particles exert forces on each other. Okay, so these particles actually have forces that act in between them. These forces can be attractive and these forces can be repulsive. 4. The energy of a particle's motion is kinetic, okay, and their collisions are perfectly elastic. So this tells you that when particles collide, the collisions are perfectly elastic. So that's for KMT. Now the 5th postulate states that the average kinetic energy of the particles is directly proportional to the absolute temperature, meaning higher temperature, okay, translates to faster average motion. The higher the temperature, the more the particles move, the faster they move, okay. Now let's look at KMT and the 3 states of matter. So for the solid state, we know that the particles are fixed, they are ordered, they are tightly packed in a regular lattice, okay. But take note, for a solid state, the particles actually move, but they don't move from one place to another like the others. They vibrate around a fixed position. And so for solids, we can say kinetic energy is less than intermolecular forces. So the value of the kinetic energy is less than the value or the strength of the intermolecular forces. Okay, now solid particles have definite shape and volume. They have a high density and they are incompressible. That's a generalized view based on KMT. Now, based on KMT, you look at liquids, and we can say liquids particles are closely packed. That's they are close together, but they are disordered. That's it for liquids. And the particles can move past one another. That's they can slide past one another. So particle motion. So for particle motion, so particles have more kinetic energy than solids. So this allows them to flow, okay, and this also allows them to slide past each other. So for liquids, we can say that the kinetic energy is approximately equal to or very close to the value of or the strength of the intermolecular forces. Okay, now for the macroscopic properties of liquids, so they have definite volume, indefinite shape. Take note, they have definite volume but indefinite shape, that is, they take the shape of their container. Also, they have higher density compared to gases, which we'll be looking at, and they are nearly incompressible. Some are nearly incompressible based on KMT. Now for gases, so particle arrangement. So the particles are far apart, that's for gases, and they are completely disordered. Completely disordered. Now to particle motion. So particles in gases move in rapid, random, straight line paths. Take note of that. Rapid, random, straight line paths until they collide. And so for gases, the value of kinetic energy is greater than the strength of the intermolecular forces. Okay. Now for their macroscopic properties, so they do not have definite shape or volume. They only expand to fill the container. Okay, so that is noteworthy, and they have low density and they are highly incompressible. Highly compressible rather, highly compressible. So you might have seen in the case of our cooking gas and all of that, the LPG. So gases are compressible. Okay, now let's look at temperature and some other key points. So temperature is a measure of the average kinetic energy of the particles in a sample. So take note of that. So while heat is the total energy transferred due to temperature difference. So heat is the total energy transferred due to temperature difference. Okay, so that's the difference between heat and temperature. Now we look at the Maxwell-Boltzmann distribution. So not all particles move at the same speed. So from the Maxwell-Boltzmann distribution is a graph that shows the distribution of kinetic energy or speed among particles at a given temperature. So that is the Maxwell-Boltzmann distribution curve. Okay, so the curve starts at origin, that's 0, even though no particles have 0 energy, but it starts at 0 and then rises to a peak which represents the most probable kinetic energy, and then falls off gradually, showing that few particles have very high energies. Okay, so the area under the curve represents the total number of particles. Okay, now let's just link the concept of what we've just talked about in this module. Now for the kinetic energy, that's KMT, kinetic theory of matter. So this is the foundation for what we're looking at next on gases. Okay, so common misconceptions: particles in a solid don't move. No, they actually move, but it's vibrational motion and they move around a fixed point. Secondly, when a substance is heated, the particles themselves expand. No, so this is false. Actually, the particles don't expand themselves. Instead, the particles move or vibrate more. Okay, then for the Maxwell-Boltzmann distribution curve, so for the Maxwell-Boltzmann distribution curve, Yes, I think I've jumped. Okay. So the definition shows that no particles have low energy. No. So the particles show that there's a range of energies. Okay, range of energies. So 4, temperature measures the total heat energy. Actually, temperature measures the average kinetic energy. Average kinetic energy. Okay, so that is it. We move to the next module. Module 3. Module 3, and then okay. So we look at properties of gases. Properties of gases. So we are going to look at gas pressure. We're going to look at the gas laws, Boyle's, Charles and Avogadro's law. You're going to look at the ideal gas law and just relate it or link it to KMT. Now, what is the real world relevance? So, why does a hot air balloon rise? Okay, why does it rise? Then, why do we predict weather patterns? This should be able to answer the question. Why must scuba divers be concerned about the bends? Okay, scuba divers, deep ocean divers. Then all these questions are answered by understanding the properties and behavior of gases. So, gases are part of our daily lives. We breathe in, breathe out. Okay, it's all around us. Without gases, we will not survive. Okay, so there will be no life on this planet. So, and there will be no intelligence without gases. Okay, in fact, we use gases also even in our own daily lives. Okay, for instance, our cooking gases. Nowadays, vehicles are run on gases. Okay, industries on gases. So gases are all around us. Okay, the weather, the gas, and all of that, pollution, taken up by gases and all of that. So gases are all around us and they are important in our daily lives. Okay, now to the theoretical foundation and mathematical formulations. Okay, so pressure, we start with pressure, which is defined as force exerted per unit area. So gases actually, one of the things you know about gas is that it's related to pressure. Okay, because pressure even determines its properties. Okay, so what are the units of pressure? Atmosphere, millimeter mercury, Pascal, bar, and look at the conversions. Okay, so please acquaint yourself with the conversion. I can ask you in the exam condition, how can you convert 3 atmosphere to millimeter mercury? How can you convert 5 atmosphere to torr? Okay, how can you convert 10 atmosphere to Pascal? Okay, or how can you convert 50 atmosphere to bar? Okay, so acquaint yourself with this. Now to measurement. A manometer measures gas pressure relative to atmospheric pressure, while a barometer measures atmospheric pressure. So you should be able to differentiate between a manometer and a barometer. Okay, now we move to the empirical gas laws. Empirical gas laws, I'm sure you are familiar with these. Now, Boyle's law. Boyle's law, the volume of a fixed amount of gas at constant temperature is inversely proportional to its pressure. That's Boyle's law. So we are linking that's pressure and volume. Okay, while you keep the amount and the temperature constant. Okay, a fixed amount of gas at constant temperature. Now we look at Charles' law. Charles' law, the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature in Kelvin. So you are linking volume and temperature for Charles' law, while you keep amount and pressure constant. Okay, now for Avogadro's law, we are looking at constant temperature and pressure. Okay, the volume of a gas is directly proportional to the number of moles of gas. So this time you are keeping both temperature and pressure constant while you are linking temperature and amount in moles. Okay, so that's how it works. Okay, now look at ideal gas law. So you're familiar with PV is equals to nRT. Okay, so this is important. In fact, PV over nRT must be equal to 1 for you to call it ideal. Okay, so ideal gas is a hypothetical gas that perfectly follows the ideal gas law. Okay, so it's hypothetical, meaning that it is, let's say, imaginary. Okay, so the another word is perfect gas. Okay, so it assumes that gas particles have no volume and experience no intermolecular forces. So take note of these characteristics of the ideal gas. So ideal gas, for an ideal gas, the gas particles do not have volume and they do not experience intermolecular forces. Okay. Also, the collision of the particles are always perfectly elastic. So, but for real gases, okay, real gases are not, of course, they are different from ideal, okay, but there are times that real gases can behave ideally. So take note of this point too. Real gases behave ideally at high temperatures, okay, and low pressures. High temperatures and low pressures. That's the condition for a real gas to behave ideally. Okay. Now we move to Dalton's law of partial pressures. So in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of partial pressure of the individual gases. Okay. So if you have two gases, okay, and A and B, so what he's just saying is that the two and A and B must not react. If A and B are not reacting, we can then say that the total pressure exerted by a mixture of A and B is the sum of the partial pressure of A and the partial pressure of B. Okay, so that is what this is about. So KMT, you can read this up, the relationship between KMT and what we just studied. So what are the common misconceptions? So a mistake you can make is using degree Celsius instead of Kelvin during gas law calculations. Okay, so that's a big mistake. Another misconception is when you say gases have no mass or weight. No, that's not true. Gases have mass. Okay. Next, all gases behave ideally under all conditions. This is false. As I said, real gases can behave ideally, okay, at low pressures and high temperatures. Or real gases deviate from ideal behavior at high pressure and low temperatures. Okay, now there are gases that are close to being ideal than others. And for instance, noble gases and diatomic gases like nitrogen gas and oxygen gas are most ideal. Now, confusing total pressure and partial pressure. Yes, they are different. So partial pressure is the contribution of the total pressure of one gas. Okay, while we talk about the total pressure referring to the sum of all the partial pressures from the individual gases. So that is what this is about. Okay, move to the next module. Yes, module 4, we look at equilibrium. So equilibrium. Now equilibrium, we know that okay, chemical equilibrium is a dynamic state where the forward and reversion rates are equal and concentration remains constant. So what is just telling us, okay, for during chemical equilibrium, okay, the forward rate is proceeding at the same rate as the reverse. So you have a forward and reverse reaction. Forward and reverse. So as the forward reaction is taking place, the reverse reaction is also taking place at the same time and at the same rate. Okay. And what happens is that for a viewer looking from outside, that viewer might think nothing is happening because, of course, there might color might remain constant and some other things, but this is dynamic equilibrium. Okay, the reaction is proceeding. Okay, and that is because, but you cannot see any net change per se. Okay, over time because the forward reaction is occurring at the same rate as the reverse reaction. Now, real world relevance. Why does a can of soda go flat after you open it? How do our lungs efficiently absorb oxygen from the air? Okay, so these processes are governed by the concept of equilibrium. Okay, so these are real world relevance. Okay, so and in fact we can see it in other industrial processes. Okay, in how oxygen binds to hemoglobin and in many other everyday phenomena. Okay, now to the theoretical foundation and mathematical formulation. Okay, so for dynamic equilibrium, this is a definition you can use. It is the state where the rate of the forward reaction equals the rate of the reverse reaction, resulting in no net change in the concentrations of reactants and products over time. Okay, so that is it with regards to dynamic equilibrium. Now we move to equilibrium constant K. Equilibrium constant K. This is a big K, okay, capital letter K. Now, equilibrium constant K, there you have, let's say you have AA, you can see there, law of mass action, BB, giving you CC and DD, okay. So, where the small letter refers to the number of moles, while the big letter refers to either the product or the reactant, okay. Now, to get your equilibrium constant, what you now have is C, okay, C capital raised to the power of small c times D capital raised to the power of small d all over A capital raised to the power of small a times B capital raised to the power of small b. So take note of that. Now, concentrations here are in molarity. So, and in this case, only aqueous and gaseous species are included. So, take note of that for K. Now, to interpret the magnitude of K, okay? So, when K is far greater than 1, the reaction favors the formation of products at equilibrium. But when K is far lesser than 1, the reaction favors the reactants at equilibrium. So that means to shift towards the reactants. Now, when K is approximately equal to 1, then significant amount of both reactants and products are present. Okay, so take note of that. So for K, we don't consider pure solids and pure liquids in the equilibrium expression. Okay, now we move to reaction quotient. Reaction quotient is as the exact form of K. Okay, but the only difference is that it is calculated using the current concentration of reactants and products, and this may not be at equilibrium. So now, how do you compare Q to K? Okay, this can also come out in an exam. How do you compare Q to K? So when Q is less than K, there are too many reactants or too few products. So when Q is less than K, the reaction will proceed in the forward direction, okay, to reach equilibrium. But when Q is approximately equal to K, the system is at equilibrium and no shift will occur. Now, when Q is greater than K, that means there are too many products and too few reactants. So now the reaction will proceed in the reverse direction to reach equilibrium. Now, this brings us to an important principle, Le Chatelier's principle. So Le Chatelier's principle, so it says that if a system at equilibrium is subjected to a change in condition, okay, change in condition, which can be stress, so the equilibrium will shift to counteract that change and restore a new equilibrium. That is it. Okay, now let's look at the different stresses, okay, that can happen to a system at equilibrium and how that system will respond to counteract it. Okay, now we look at change in concentration. So when you add a reactant or product, okay, to equilibrium, it will shift the equilibrium away from the added component. So if you add a reactant, take note, okay, that means you get more product. If you add more of the product, you will get more reactant. Then the second one is now removing. Take note of this, removing. So when you remove a reactant, you get more of the reactant. When you remove product, you get more of the product. That is for change in concentration. Now to change in pressure, that's for gaseous reactant. So you look at where you have moles of gases. So you look at the number of moles of gases on the right and number of moles of gases on the left. Okay. So what will happen is when you increase pressure, okay, so the equilibrium will shift to the side with fewer moles of gases and when you decrease pressure, the equilibrium will shift towards the side with more moles of gas. So that is it with pressure. Now look at temperature. So temperature depends on whether it is endothermic or exothermic. So if it is endothermic, okay, that is delta H is greater than 0. So then increasing temperature will shift the equilibrium towards the product. Increasing temperature shifts equilibrium towards product. But for an exothermic reaction where delta H is less than 0, increasing temperature shifts equilibrium towards the reactant. Okay. Now adding a catalyst is of no use here because to speed up both the forward and the backward for reverse reaction. Okay, read up on the linkage. Let's look at the misconceptions. So misconceptions at equilibrium, the concentration of reactants and products are equal. So no, it is the rates that are equal. The rates are equal. Okay, the rate of the reverse and forward reactions are equal. Now a reaction at equilibrium has stopped. No, that is why it is called dynamic equilibrium, dynamic moving. So it is actually the reaction is occurring, it's just that the forward and reverse rates are occurring at the same time and at the same rate. So 3, changing temperature changes the concentration, so K must be constant. So K is not constant with temperature. Okay, so a catalyst can change the equilibrium position. No, a catalyst when introduced to equilibrium, so it will affect both the forward and reverse reactions. Okay, now we move to our last module. Yes, module 5. So module 5, we are looking at redox reaction. First of all, we need to ask us, remind ourselves of some key principles here. Okay, so now let's look at oxidation. Oxidation is the loss of electrons. It's the loss of electrons, and reduction is the gain of electrons. Okay, so you can also use oxidation number to track, okay, electron transfer and identify reduction processes. So with oxidation number, you can also know whether oxidation has taken place or reduction has taken place. Okay, now we also look at balancing half reaction, balancing redox reactions. Then we'll briefly look at galvanic cells. Okay, so now to the theoretical foundation. The real world relevance, we look at why do metals rust, how do batteries power our phones and cars, okay, how do our bodies extract energy from food. So this is under the purview of this course. So it's something I would like you to check out. Now, theoretical foundation and mathematical formulations. So remember I said oxidation, loss of electrons, reduction, gain of electrons. Okay, so I'm called an oxidizing agent the species that accepts electron and is itself reduced. A reducing agent is a species that donates electrons and is itself oxidized. Okay, take note of this point. Now let's look at oxidation number. I'm sure you've done this at O level. So, but take note of the rules for assigning oxidation numbers. 1. Oxidation number of an atom in a pure solvent, a pure element, is 0. So once it is not mixed with another element, okay, so once it's only one element, okay, it is 0. Now we look at oxidation number of a monoatomic ion. So the oxidation number of a monoatomic number is equal to its charge. So for Na plus is +1, O2 minus is -2. Okay, so normally oxygen will have -2. Okay, you assign -2, while fluorine you assign -1. Hydrogen is usually +1, but when it's bonded to a non-metal, sorry, yes, when it's bonded to a metal, it takes -1. Okay, now the sum of the oxidation numbers in a neutral compound is 0. Okay, so then also the sum of oxidation number in the polyatomic ion is equal to the charge of the ion. Take note of that. So now let's move on to, okay, okay, I think this is where we are actually going to do our major work before we end the class. So one, you look at how to balance redox reactions. Okay, so here are the rules for acidic solution, and you have rules for basic solution, but I'll delve into that before we close the class. Now look at galvanic cell. So what is a galvanic cell or voltaic cell? So it is an electrochemical cell that uses a spontaneous redox reaction to generate electrical energy. Okay, that's what you get in your batteries, right? So now anode is where oxidation occurs, cathode is where reduction occurs. Okay, so and the anode is a negative charge for a galvanic cell, while the cathode bears a positive charge for a galvanic cell. So there is also a salt bridge. So a salt bridge is a U-shaped tube containing an inert electrolyte. Okay, it maintains electrical neutrality. So, but it allows ions to flow between half cells without mixing the solution. Very important. Okay. Okay, so look at cell notations, how to write. Okay, so for instance, you can, when you're writing a cell notation, you put the anode, then the anode ion, cathode ion, then the cathode. So if you look at zinc, you can see how zinc is written. Zinc, first of all, zinc, solid zinc, then zinc 2 plus aqueous, then you have a double line, then copper 2 plus aqueous, and copper, solid copper. Okay, so take note of that. Now, how do you balance a redox reaction? So let's look at this. Okay, an example here will be okay. Remember, we've talked about the rules before. Okay, the rules for balancing redox reactions. So balancing redox reactions. So here we saw the rules for acidic. So now we are going to look into it in a greater detail. Okay, now this is how I'll be sharing this material with you. This is how to balance redox reaction. Okay, so you learn and practice. Please try to practice. Okay, see how this is done. So you have so you have three conditions. So one, without hydrogen or oxygen. Second one in acidic solutions. Third one in basic solutions. So we are going to look at the three conditions. So first, without hydrogen or oxygen. So when in this kind of reaction, no hydrogen, no oxygen, and all of that. So what you can do is you first of all find out which species in this reaction is being oxidized, which species is being reduced. So remember, when it is pure K 0, only Br2, pure Br2, bromine gas 0. It's not mixed with another element. So they both have 0. Okay. But at the end of the day, you have KBr. KBr is K plus Br minus, right? So K plus means that your K is +1, your Br minus is -1. And if that is the case, that means the oxidation number for K has reduced, potassium has increased rather, while the oxidation number for bromine to bromide has reduced. Okay, and so we can say that potassium has been oxidized while bromine has been reduced. Okay, so if that is the case, you just follow this step. Okay, you separate K0 to this as they did here, then Br2 to this, and then you balance it out. You can see balancing out here. Okay, so and then that is why 2 was added here. So this Br2, so you need to balance it. So that's 2 Br2. Okay, you need to balance first of all the elements, balance the elements before you balance the charges. So now we want to balance the charges. So we see that this is K0, and so here you only add electrons. Okay, only add electrons. And if you add the electrons, you just need to add one electron here so that it will be 0. This side is 0, and this other side too must be 0. That's K0, and you have K plus. So to make the other side 0, it will be, so you have 0, then the other side is +1. That K plus, let's take it as +1. So how can you make +1 0? Is you add -1, right? So +1 minus 1 is 0. So to do that, +1, then -1 will come from the electron. Okay, now look at bromine. Bromine, you have 0 and you have 2 minus, or -2, mathematically speaking. So you want to balance it, 0 and -2. So what you can do is to add -2 to 0 on this side. So when that -2 will come from electrons, right? So that's why you have Br2 0 plus 2E minus, and it gives you 2 Br minus. So you can see what was done there. So but remember that here we have 2 Br and all of that. So what you want to do is to ensure, okay, that you can mix both of them. To mix both of them, you must first of all ensure that the electrons, okay, also match, and that's why you have um 2 times, okay, 2 times, you can see 2 times here. So to make it 2k naught is equals to 2k plus 2e minus, and so you can mix both equations now. When you mix both equations, you now see that the electrons will cancel out, and then you have 2k 0 plus Br2 0, giving you 2k plus 2Br minus. So that's it. Okay, so try your hands on these other examples we have here. So you can see some other examples. Now move to acidic medium. So acidic medium, what you are doing is you also want to balance out. Okay, I need to also look at which one is being reduced, which one is being oxidized. So you see that Cl here is plus 5, O is minus 2, I2 of course is pure 0. So I after the arrow is plus 5, O is minus 2, and Cl minus, of course, minus 1. If that is the case, then we can say, okay, we can say iodine has been oxidized and chlorine has been reduced. Okay, iodine has been oxidized and chlorine has been reduced. So having that at the back of mind, so you can now separate the one that has been oxidized, okay, that's the iodine, and the one that has been reduced, chlorine. So you can see how we've separated them, and then now try to balance the equation. Okay, so except for hydrogen and oxygen, so you try to balance it, and you can see, so just for discounting us or forget hydrogen and oxygen for now, and try to balance the other elements. So that's why 2 was added to iO3. Now we move on to how to balance oxygen. To balance oxygen, okay, so you can see that water was added. So you add water to balance oxygen. Then to balance hydrogen, you add protons. That's H plus. Okay, you have protons, H plus. So that is what you get. Okay, and then next you add your electrons to it as we did in the other one. Okay, to balance both the oxidation reaction and the redox reaction, and then you ensure that, okay, they match each other. That's why you have the 3 times above, okay, so that they can match each other. Okay, and the other one is 5. So by the time you do 5, and you end up with 30 E, okay, here, and 30 E2 below. So 30 E minus up, 30 E minus below, and with that you can now mix both of them to get your overall reaction. So that's how it works. Now to basic reactions. So for a basic reaction, so you do the same actually. Okay, you determine which one is being reduced, which one is being oxidized. You do the same thing. Okay, you do the same thing. So that is it. Okay, so can practice and practice. Okay, now we come to the end of my section of this course. So I'll be taking one class to round up. Okay, and it might be a general class, if possible, a general class. Okay, so I wish you all the best even in your exam, as you prepare for your exam and your tests. Okay, so have a lovely day.